Okay. So first thing is no class on Monday. I won't be here on Monday. That's right. No, maybe the next week. No class Monday.
Will there be any assignments due on Monday?
No, it'll be due on Wednesday. That's why I got to get through some stuff today, so I can give you some problems for. And then let's look at this one. All right, so I'm just going to go through the steps and we'll worry about the centroid stuff when we get to it. So step one, is there a fixed point? Yes. And so A is the hinge or the pin. And so we have to calculate that mass moment of inertia. Okay, so that's the first thing that gets tedious here. So we need the mass moment of inertia about that fixed point. Okay, so how do we have to do this? Well, we need, so we can think of it as a rectangle minus a circle. Okay, so I'll think of this as shape 1, this is shape 2. And so for shape 1, the moment of inertia about A is the moment of inertia about the center of mass of the rectangle. And then you have to use the parallel axis theorem plus md squared, where d is the distance from the rectangle center of mass to the pin. And then we'll do shape 2. So the moment of inertia of shape 2 about the pin is the moment of inertia of the circle about its center of mass. So I'll call this IA1, this is IA2, this is 1, this is 2, plus md squared, where this time d is the distance from the center of mass of the circle to the pin. And all this takes a little geometry and trigonometry and stuff. Okay. And then once you have those, the total mass moment of inertia about A is equal to the mass moment of inertia about A of the rectangle minus the mass moment of inertia about A of the circle. Okay. But the steps in there that I didn't do are a little time consuming. And then we have the free body diagram. We have a weight force here so to calculate that weight force, you need to figure out where the center of mass is. And this is mass times 9.81. And then you have a reaction force due to the pin. I'll call that R. And then it says, besides the weight, there's an external couple of 100 Newton meters applied. Well, it doesn't matter where you put this. The location of a couple doesn't affect anything on a rigid body. It's probably going to be applied here, so I would tend to draw it there, but it doesn't change the problem to draw it somewhere else. So this is 100 Newton meters. And then you do your table. For the R vector, rho is 0. The force is Rx, Ry. Cross product is 0. For the weight force, I don't know what that rho vector is. I'm just going to call it scalar rho x, scalar rho y for the components. The total mass is 50, so this is 0, negative 490.5. Then the cross product is negative 490.5 rho x. But that's not a variable. You know what that rho is. So this is known once you find the center of mass. And then the last one is the couple. We don't care about these. That's positive 100. Do we need Newton's second law for this one? No. So then go to step 6, rotational Newton's second law. We know all this stuff, so we can calculate the angular acceleration. And then, really everything about this is the same as other problems, except that it's trickier calculating the moment of inertia and calculating the center of mass. Then once you get this, it asks you to calculate the acceleration vector of various points, and you'll just do that as the acceleration is equal to alpha cross r plus omega cross quantity omega cross r. And I think it asks you to do that for all 4 corners, so you have to do that 4 times.
Just change the radius, right?
You just change that R vector, yep. What's the definition of the R vector?
The center of rotation to the
Center of the circle, the circular motion or the spherical motion. Always circular with this rigid body stuff because we're in 2D. Center of the circular motion to the point you care about. And so what's the center of the circular motion here?
6 point.
Yep, exactly. So everything is moving in a circle around that. And so you need, well, the acceleration at this point has 0 r, and of course that's not accelerating, it's not going anywhere. But for this one, you'd need the vector from the pin to here. It's possible you could make this problem, you could definitely make it slightly easier. It might make it a lot easier. I'm not picturing super clearly right now. Just the calculations of the moment of inertia and the centroid and stuff like that. It might be worth it to use sort of a funky coordinate system with x going this way and y going this way. Z is still coming out, so it doesn't change that. Otherwise, you just have to use a lot of cosines and sines at 20 degrees. Yes?
So, like,
Yesterday or Monday's homework, there's a couple of problems where some of them didn't say that there was an external moment on them.
Mhm.
And it seems like if it's not explicitly said there's a moment, we should assume there's none.
Correct.
Rather than normally want just from it rotating.
Right. Remember that. So remember this. This is really helpful when thinking about joints. Remember that joints don't provide motion; they restrict motion. Okay. Um, so I think what people often sort of think, and it's kind of subconscious or whatever, but you think, okay, this thing is free to move, so there should be a moment that's making it move. It's the opposite of that. If it's free to move, there's no moment because there's nothing restricting that rotation. Okay. If it's not free to move, that's when a moment has to be provided to keep it still. You know, like this wall is applying a joint. You know, there's a joint between the wall and my hand. Okay. What that wall is doing is it's, in order to keep my hand from moving that way, it's applying a force, you know? And so always think of that. Those loads restrict motion. They don't provide motion.
So like,
I mean, they can also
in
provide motion.
this example, if like let's say the pin got rusted up and
Yeah.
it couldn't
Yeah.
couldn't go down, then
Right.
there would be a moment.
Correct. Yep, exactly. Or even if it rusted and just didn't provide motion, frictionless motion anymore, yeah, there'd be some kind of moment. It just might not be enough to totally stop the motion.
But if it's totally free, then there's no moment.
Right.
Okay.
And so if I draw something like this, that always means no moment unless it says explicitly. You can also just think, you can also just kind of, we use pin joints so much. Just remember that a pin joint without friction always just applies an unknown force vector, and that's all.
If it was a three-dimensional example, there would be a moment just in the non.
Yes, that's right. So yeah, we did that kind of stuff in statics, but we can't do that in dynamics because you need a different version of rotational Newton's second law in 3D. So we can't use this approach for that. We can only do planar stuff this way. Okay, so that is it for that one. So now I need to go into linkages. And this really is just piggybacking on rigid body kinetics. So linkages are collections of rigid bodies connected by joints that are not static. If you have a collection of rigid body connected by joints that is static, what's that called? It's not called a linkage. A truss is an example of a structure. Yep. And so I'm going to just list out a general approach to linkages, and then we'll just do a few examples.
Would be like a combustion cylinder. That's
yeah, I mean, yes, any machine of any kind that you can think of that has joints and it's not static is a linkage. And the ones that we're going to do are planar. So any linkage that you can think of where all the motions are in a plane are things that we'll be able to calculate. Scissors, you know, there's a lot of examples like this actually. This is a really useful thing, even though we're restricted to the plane. I think often machines are not made to have three-dimensional motions because it's hard to visualize and hard to design, you know. So like if you think of the motion of a piston in a cylinder and its crankshaft and stuff, that stuff all happens in a plane. Okay, so general approach. The linkages. Okay, so the first step here, it sounds so easy. I'm listing it as one short step, but it's obviously can be pretty time consuming. So the first step is go through the steps of rigid body kinetics for each rigid body in the linkage. So after you do this, you will have more variables than equations. And so that just means you need more equations without introducing more variables. And eventually you need the number of equations to catch up with the number of variables you have. And so the second step is the geometric constraint equations. There are really two types of joints that we're going to have. These constraint equations always happen at joints. And so at any pin connecting two bodies, you need a constraint that says the acceleration of the point where the pin is, according to body one, has to equal the acceleration where the pin is, according to body two. And this will use the watermelon equation and the relative motion equations. The other type of joint you can have, so B is if a point on a rigid body rolls or slides along a surface, the component of acceleration that's perpendicular to the surface is 0. Okay, so that's just saying that this the point, that contact point is not going to sink into the surface or jump off the surface. And again, to do that, we're going to use the watermelon equation and the relative motion equations. Okay, so the first step is doing rigid body analysis for every body in the linkage. At that point, you'll have more variables than equations. And then you'll go around to each joint and apply this, come up with the constraint equations at each joint. And in the end, you'll have exactly the number of equations that you have variables. Okay, so I'm just planning to go through a bunch of examples and have you go through some examples. So let me start with something kind of simple. So let's say that we have a linkage like this. It's pin joints at both connections. And let's say that the length of both of these members is 0.5 meters. The mass of each member is 2 kilograms. At this instant, let's see. Let's say that it's at rest, so these omegas are equal to 0. And we want to calculate the angular accelerations of each member. And I'm going to apply one external force right at the midpoint of this of 20 newtons. Okay, so gravity is acting on both of these, and there's that 20 Newton force. I am going to label these this way, body 1 and body 2. And the joints, I'm going to call this A and B. Yes.
Remember, what's keeping member 1 from falling down?
Well, it is nothing. This isn't statics anymore, So, I mean, this connection is keeping it from just falling straight down to the ground. But, so what we expect to happen is this is going to go this way, and this is going to, so, it's going to sort of fold as it goes over to the right.
Okay, is the second member going to move?
It's going to, yes, it's going to have an acceleration due to this 20 Newton force.
Or isn't it the pin at the bottom, like keeping it?
Yeah, it's not going to move like this. It's just going to tip over.
Isn't there another pin at the top, like a B?
Yeah.
But it's not a fixed.
It's like,
it's just connecting it, like it's not fixed to the wall or something.
right. It's only fixed to the ground here. And so this 20 Newton force isn't going to make the whole thing move like this. It's just going to make it do this.
All right, yeah.
Okay. And as it does that, this angle is going to go from 90 degrees to less than 90 degrees. And eventually the whole thing, if you let it go through time, I mean, we're looking at a single instant, but this whole thing would just be lying folded on the ground over here.
Also, that means it's not rotating. It's just going to fall and that's it.
Yeah, I mean, it's gonna.
And that's what you mean by omega equals 0.
Yeah, right now there's no angular velocities, but there are going to be angular accelerations, and we're going to have to calculate those. But remember, we can never calculate. Well, yeah, we can never use Newton's laws to calculate angular velocities. We can only use Newton's laws to calculate angular accelerations.
And just one more question. Would this example work if we remove the 20 Newton force and if we just accounted for the weight for the force of gravity on two members to make it collapse? Would that still work?
Yeah, I'm not sure exactly what would happen. I mean, this would, at this instant,
The gravity for member two would go straight down, so it probably wouldn't. But
yeah, I'm
for
not
member
sure
one,
that this one would have any angular acceleration at all,
What about the
but
force
this
for
one
member
would
one?
go down. Yeah.
Would
So-
it be possible for it to apply like a angular acceleration through the pin?
Yeah. Mhm.
And then make member
Right.
two then collapse?
Yeah. But I mean, notice how simple this is, and thinking through what's going to happen is still complicated, you know? So anyways, we're going to go through these steps and calculate all this stuff. So I'll start with body one. Whoops, I was thinking of static, so I started with the free body diagram, but we want to go through the steps of a rigid body analysis. So does body one have a fixed point? No, it is. I mean, it does have a pin joint connecting it to body two, but for a fixed point, remember, we're talking about a point that doesn't move relative to the coordinate system. So that, that point at B, that can move. Yep.
So like I remember before with like relative motion equations, in this scenario, we would like assume that member two is fixed when doing member one, or we don't do that.
Well, no, we don't have to do that. We won't make any assumption about that. We will, so when we get to the relative motion equations, that won't be until we get to the constraint equations. Really, this won't look any different than rigid body analysis until we're done with the kinetic stuff. Okay, so there's no fixed point here. And so the about point is the center of mass of body one. And so the moment of inertia about the center of mass of one, we're just going to use the formula for a slender rod. So this is 1/12 times the mass of two times the square of the length. And so that is 1/6. So that is 0.16 repeating. Nope. That is wrong. This is 0.0416 repeating. And this is kilogram meter squared. And now I'll draw the free body diagram. There's a weight force acting at the center of mass. So that is 2 times 9.81. And then there's a pin joint at B. And a pin joint always applies an unknown force vector. So I'm going to put that in like that. And then I'm going to use the double subscript notation and name this. So this is the force on 1 by 2. So I'm going to write this as F1, 2. Okay, any questions about that? the people who took statics from me are a little more used to using this notation in settings like this, but it'll make sense soon enough, I think. And then I'll do the table, row, force, moment. Our about point is the center of mass. And so I'll start with the weight. The row vector is 0. And the force is 0, negative 19.62. Cross product is 0. And then the force on 1 by 2. What's the definition of the row vector? The vector from the about point to the force. So this is, so from the about point to the force is half of the length. So that's 0.250. And the force vector is F12x, F12y. Cross product is 0.25 F12y. Okay. Do we need to use Newton's second law for this one? Yes, because there's no fixed point. So Newton's second law, we're going to take all of these forces in this column and set it equal to the mass times the acceleration of the center of mass. Okay, so I'm going to, 0, negative 19.62 plus F12x, F12y is equal to the mass of 2 times the acceleration of the center of mass. And I'm going to call that A1x, A1y. Yes. Yes, exactly. So this is the acceleration vector of the center of mass of 1. Okay. So I'm going to leave out the center of mass in my notation just for cleanliness or whatever, but the only acceleration variables we're going to have are going to be centers of mass, so it'll be easy to keep track of. And then we have rotational Newton's second law. And so we're going to add these up and set it equal to I alpha. So 0.25 F12y is equal to 0.0416 repeating times alpha of 1. Okay, so we have our first 3 equations. I'm going to write it as, so equation star is F12x minus 2a1x is equal to 0. Equation 2 star says F12y minus 2a1y is equal to positive 19.62. And equation 3 star says 0.25 F12y minus 0.0416 repeating alpha 1 is equal to 0. I'm just getting all the variables on one side and all the constants over on the other side. Okay, well, if this was a single rigid body, we would be able to solve this now. But let's count up variables. And by the way, we don't care about about the variables we have in our free body diagram. We only care about the variables that pop up in the equations. So we'll count from the equations. So we have 1, 2, 3, 4, 5. So 3 equations, 5 variables. Okay, the variables are F12, that's a vector, so it has x and y components. A1, that's a vector, so it has x and y components. And alpha 1. Okay? Any questions about the first one?
So it's just gonna be like a huge matrix at the end of all of those.
Yeah. In this one, it won't be so huge. I mean, well, it'll be a little disheartening how big this matrix is for as simple a linkages problem as you can come up with.
I feel like we're extending to go over everybody.
Yeah. So now we'll go to body 2. I almost fell for it and drew a free body diagram again. We're doing rigid bodies. So step 1, is there a fixed point?
Yes. The one on the right.
Yes. And so A is the pin at the bottom. So now for the moment of inertia of this one, this is equal to 1/12 times the mass times the length squared plus the parallel axis theorem part, which is the mass, times the square of the distance from the center of mass to the about point, so 0.25. So that is 0.16 repeating kilogram meters squared. Okay, so the moment of inertia of the second one is bigger than the first one because this one isn't about the center of mass. And now the free body diagram. At the center, we have a weight force of 19.62. At the bottom, we have a pin. And so that's an unknown force vector, and I'm just going to write that as R. That's just the variable name I'm giving that vector. And then up here, we also have a pin joint. And this force on body 2 is the force on 2 by 1. So I'm going to write that as F21. But Newton's third law says if you switch those subscripts, all you're doing is switching the sign. And we already have defined variables F12. So instead of defining 2 new variables F21, I'm going to call this negative F12. And then we're just reusing that old variable. Okay, so the people who took statics with me are very used to this, but maybe not as used to it if you didn't. But you will get used to it. And then, oh, I forgot the external force of 20. And now that's done. Any questions about that?
What is the other one?
You're right, it is. Okay. Thank you. So now we'll do the table. And this time our about point is here. So I'll start with this r vector. The rho vector is 0. The force is Rx, Ry. Cross product is 0. Then I'll do the weight force. The vector from the about point to where the weight is applied is 0.25. So 0.25. And the force is 0, negative 19.62. Cross product is 0. Which makes sense if you think about the fact that that weight force is acting right. Its line of action is going right through that that about point. And then the 20 Newton force, it's at the same location, so the rho vector has to be the same. And the force is positive 20, 0. And so the moment is negative 5. Does it make sense that that's a negative moment? Yeah, that would cause a clockwise rotation. And then the last one is our force, negative F12. The rho vector is 0.5. The force vector is negative F12x, negative F12y. And the cross product is positive 0.5 F12x. Do we need Newton's second law for this one? No. So we'll go right to step 6. And that says negative 5 plus 0.5 F12x is equal to 0.16 repeating times the angular acceleration of body 2. Question?
Why we don't do Newton's second law?
Because there's a fixed point. So anytime there's a fixed point, you don't need it now. You might need it later. So don't erase all your notes, but for now, we're going to skip it. Okay, so this gives us, what do we have so far? 3 equations for our big system. This gives us our 4th equation. I'll count them up in a sec. So let's see, we got 0.5 F12x minus 0.16 repeating alpha 2 is equal to positive 5. Okay, so now we have 4 equations. I mentioned before that when you're adding up the variables, counting up the variables, don't look at the free body diagrams, look at your equations. Okay, all that matters is the things that appear in equations. So in our free body diagram, we have this R, but notice it didn't appear in our equation, so I'm not going to count that. So the equations that we have now are F12, not the equations, the variables. Let me write. So we have the vector F12, we have the vector A1, we have the scalar variable alpha 1, and now the only thing that we've added is the scalar variable alpha 2. So now we have 6 variables.
And just for equation.
What? And just 4 equations, so we can't do anything yet. Okay? So how do we fix this problem?
Newton's second law.
Not Newton's second law, although that's a good, that's a good thought. So now we're getting into the constraint equations. Okay, so now at any place where, so we're gonna, for constraint equations, we're gonna look for any places where either two bodies meet, that's at B, okay, and or any place where a body is rolling or sliding along a surface. That's not happening anywhere. So the only place that we have constraints here is at B. And what we're going to do is we're going to say that this point on body 1 has to have the same acceleration as this point on body 2. It makes like perfect intuitive sense, right? I mean, basically what we're saying is don't let these things fly around freely. They're locked together there. Okay. So now we're going to do our constraint equation at B. And so I'm going to calculate the acceleration of that point B on body 1 and on body 2. And after I do that, I'm going to set the two equal to each other. How many equations is that going to give us? 2, because it's an x and y component. And so notice that that's exactly as many equations as we need for our equations to catch up with our variables. So we need 2 constraint equations. So I'll start with body 1. How are we going to express the acceleration of the point B on body 1? Well, we don't have a fixed point, so we're going to have to use the relative motion equations. So we're going to say that the acceleration of B relative to the ground is equal to the acceleration of B relative to what point? Center of mass, and you'll see why in a second, plus, for relative motion, this has to be the acceleration of the center of mass relative to the ground. And the reason that we're doing this with the center of mass, I mean, there's no law that that's what we have to do, except that this is already a variable. This is our A1. So we can do this without any new variables coming in. Okay, and then this one is the watermelon equation.
Well, we don't know. Oh, okay.
Yeah, I mean, we don't know those values, but we have those variables. So we're just coming up with more equations using the same variables. Okay, so the acceleration of B relative to the center of mass is equal to alpha cross R plus omega cross quantity omega cross R. Our alpha vector is 0, 0, alpha 1. That's the variable we've already defined. Our R vector, it's from the center of the circular motion to the point we care about. So in this case, that's from the center of mass to the point B. So this is going to be 0.2500. Body 1, yeah. So first we're doing body 1 here. Yep. And then we're given that this is 0. So the acceleration of B relative to the center of mass is 0, 0, alpha 1 crossed with 0.2500 plus this thing that's equal to 0. And so you get 0, positive 0.25 alpha 1, 0. Okay, question?
So if we're doing those cross products in our calculator with a variable in it, do we,
If you have an 84, an 83, or an 86, you cannot do that. If you have a 89 or an Inspire, yes, you can.
okay, do we just put like a placeholder, like number in there?
That's one way you could do it, yeah. Or you could just remember that the way you do this, that you can do this is cross these out, and it's this times this minus this times this. Then cross this out, and it's negative of this times this minus this times this. Cross this out, and it's this times this minus this times this. It's probably faster to just remember how to do it, you know.
Wouldn't that be negative?
It's because y always has to be different. The y component is negative of,
Oh, there's another negative in there.
there's another negative, exactly. Okay, not quite done yet. So the acceleration of B relative to the ground is this. Plus the acceleration of the center of mass relative to the ground, which is a1x, a2x, 0. And if you put these together, you get a1x, and then the y component is 0.25 alpha 1 plus no, this should be a1y plus a1y, and then 0. Okay? Any questions about that?
Where are the two equations?
Well, it's not an equation yet because this was just the acceleration of B on body 1. Now we have to do it for body 2 and set them equal to each other. So now I'll go to body 2. This one's a little easier. This one has a fixed point, so we can just use the watermelon equation. So the acceleration of B is alpha cross R plus omega cross quantity omega cross R. Alpha is 0, 0, alpha 2. R, so R is the vector from the center of the circular motion to the point we care about. So this is 0, positive 0.5, 0. Omega is 0. And so the acceleration of B is 0, 0, alpha 2 crossed with 0, 0.5, 0 plus this piece that goes away. And so you get negative 0.5 alpha 2, 0, 0. So now put these two together, and you have one equation that says A1x is equal to negative 0.5 alpha 2. And a second equation that says 0.25 alpha 1 plus A1y is equal to 0. And the third one says 0 equals 0, which, this obviously doesn't help us solve a system of equations. And so this gives us our equation 5 star. A1x plus 0.5 alpha 2 is equal to 0. Yes?
So when we're writing acceleration of B, is it acceleration of B relative to ground?
Yeah,
Okay.
right. Anytime you don't see the relative motion notation, it means relative to ground. And then equation 6 star says 0.25 alpha 1 plus A1y is equal to 0.
But to get to these equations, you just equal like both of the acceleration of
Yep.
B relative to ground.
Right. So I took this one, this vector, and set it equal to this vector. And then I just rearranged it because we're going to use reduced row echelon form to solve this system. But now we have 6 equations and 6 variables. So reduced row echelon form to solve the system, the Dagobah star system. I felt millions of voices cry out.
Internally.
Did 7 times 6?
So yes, exactly. So we're gonna, it's 6 times 7. We're gonna have 6 rows and 7 columns. Yes.
So you go up a little bit.
Mhm.
The A that we just got from doing this Marlowe equation, is it A2x? This is an
Yes.
A1 for the first body?
Well, what I did, there was no A at all in the second one because it had the fixed point. So this is the acceleration of B according to body 2. See my cursor?
Yeah.
And so there's no A at all in that. And then I set this vector equal to the vector that I got from body 1. Okay, so we're going to go 6 rows and 7 columns. The equations are 1, 2, 3, 4, 5, 6. You know, these are the start equations. And then you can put your variables in any order you want. So this is F12X. This is how I'm going to do it. F12Y, A1X, A1Y, alpha 1, alpha 2. That's all the variables. And then this one is going to be the constants.
Realistically, you can put these in any order, right?
Yes. Okay, so let's go through. Let's see. So equation 1, F12X, we have 1. A1X, we have negative 2. And everything else is zeros. I'm not going to fill it in, but when you enter this matrix in your calculator, you have to fill that in. Equation 2, F12Y, we have 1. A1Y, we have negative 2. And then the constant is 19.62. You have to get those constants over on the other side of the equation. So this is 1, this is negative 2, and this is 19.62. If you don't get your constants on the other side of the equation, your answers will be backwards. And if you do some on the other side and some on the same side, your answers will be nonsense. Then equation 3, F12Y, we have 0.25. Alpha 1, we have negative 0.0416. I already forgot. Was it 0.25? Okay. 0.25. You get out of here. Okay, so 0.25, negative 0.0416 repeating. And that was all. And now equation 4, F12X, 0.5, alpha 2, negative 0.16 repeating, and 5. Oh, my computer. Okay, so this is 0.5. This is negative 0.16 repeating. And what was the constant? And now we're on the constraint equations. Equation 5, A1X, we have 1. Alpha 2, we have 0.5. And then for equation 6, alpha 1, we have 0.25. A1Y, we have 1. Everything that's not filled in is a 0. And so here's what reduced row echelon form will give you. It'll give you a matrix back that's the same size. One, two, three, four. 1, 2, 3, 4, 5, 6. And the first 6 by 6 matrix on the left is going to be just the identity matrix. That's how you know it worked, if this comes out to be the identity matrix. Why did I start filling in zeros? Yeah, exactly. Can't stop now. I'm not a quitter. Okay, so that just tells you that it worked. But then what you care about is the values. And this will say 7.5, if I did it right, 4.905, 3.75, negative 7.36, 29.43, negative 7.5. And what that means is these are the values in the order that you entered them in your matrix. So this is F12X, F12Y, A1X, bless you, A1Y, alpha 1, and alpha 2. Okay, so what that says is this was our setup. And it says that the body connected to the ground is going to have a clockwise angular acceleration of 7.5 radians per second squared. Does that make sense? And then this one is going to have a counterclockwise angular acceleration of 29.43 radians per second squared. Does that make sense? Yeah. So this one is going to get kind of whiplash with an extra angular acceleration because it's the participation of gravity making it accelerate that way, and this closing that angle, making it snatch that.
Can you look at right hand for different so you can see?
Oh. This one is this way, so it's negative. So, this is going to take some repetitions to get it ingrained, but hopefully you also see how cool this is. I mean, all these complicated interactions between bodies, this by itself gives you the tools you need to calculate the motion. Yep.
So is this the acceleration only at that one point in time, and the acceleration?
Yes, exactly. So if you wanted to see what happened over time, you could do this at a bunch of instants, and then you could numerically integrate it, to figure out how angular velocity changes over time and stuff like that. Really what you would probably do is you would write a computer program that does this at various points and then feeds that into your integration thing. But yes, anytime you use Newton's second law or rotational Newton's second law, you're doing it at a single instant.
Can you go over how you got equation 5 again?
Yeah.
Are we going to do systems problems where we have to measure it over a variable amount of time?
I don't think there are any like that. I can't remember any like that.
How the angular...
Yeah, I know what you mean, yeah.
Relate to time?
I don't think so. Okay, well, 5 and 6 I got the same way. I calculated the acceleration of B on member 1 using relative motion in the watermelon equation, and that's an X and a Y component. You with me on that?
Yeah.
And then I went to body 2, calculated the acceleration of the point B on body 2. That gave me an X and a Y component, and I set those two vectors equal to each other. So that gives me an X equation and a Y equation.
What will be the X component for the body 2? Or do you just set that equal to 0?
Well, I took this from body 1 and set it equal to this for body 2. The Y component for body 2 is is 0. So sometimes that kind of thing will happen.
Okay.
Any other questions? Okay, that's all. So I'll give you a few of these to do for Wednesday. Try to do them because you really learn by trying to do these, but I'd be happy to go through any of them on Wednesday also. Okay, that's all.